me get some chalk. This one was good. So we were talking about this black holes last time, right? Is there any question before we continue where we stopped? So where we were at, right? So we had the black hole, and there's the singularity here, right? The horizon, and I start telling you, suppose, right? There was this initial question. Suppose psi is the quantum state of the matter black hole, and then we saw that actually the black hole is not really completely black; it irradiates, right? There is Hawking radiation, and one way to think about this Hawking radiation is like creation of pairs, where one inside the horizon, the other outside, and this looks like thermal, right? Particles which radiate out of the black hole, and therefore the black hole loses mass with that, right? But then, if you wait long enough for the black hole to completely evaporate, if this is really just a thermal radiation, then you go to a mixed state, right? It's just the thermal state of all this quantum of energy that was radiated, and that would be weird because we could do, we could just completely decouple this from the rest of the universe, the physics of the universe, and this could be like a break of unitarity, right? So if you want to keep unitarity, there should be a unitary doing that, and therefore we would expect this guy to be pure, right? If there is a unitary, that's the question, then rho should be pure, right? And what rho should be? Well, should be, actually last time I said it should be psi, but therefore psi is, depends how you define psi, but suppose psi is the state, the quantum state of the matter before you put in the black hole, then there can be some dynamics inside a black hole, right? Which is just the time evolution of the black hole. So if there is some unitary description of the process, there will be some unitary applied to psi 0, right? So that's the question. Is that the case or not, right? And if this proposal, if this is indeed what happens, that would be nice, because then, from the outside perspective, the whole process is still like a unitary, so it can be described by quantum mechanics. That would be good. We have to explain how, right, Hawking radiation is compatible with that, right? Because indeed, this computation can do with quantum field theory here gives that these guys, right, they look like thermal. Answer to that, right? So this is what we were seeing last time. So is this page toy model for the black hole? Maybe we can call this psi-f, right? It's the state after the black hole dynamics. And in this toy model, we just assume that it's psi-f. It's just a state, we take it uniform from the Haar measure. What I want to do first, we will see many properties of this state, but the first thing, let's just see if that's the case. So what is the idea for that? Well, the Haar measure is just this, right, uniform measure over all quantum states, but we think it reproduces well the properties of some quantum chaotic system. So if in this U is the unitary evolution from whatever Hamiltonian describes, right, the black hole formation and evaporation process. There are reasons to believe, like, for example, if you believe string theory is the correct theory of nature, or ADS-CFT, that it should be a highly chaotic Hamiltonian. So it indeed has many features of the Haar measure, and we're just going to approximate by it for simplicity here, and because we don't really know the Hamiltonian there, right, in detail. Then the first thing that I told you last time, and we're going to prove later, is just that suppose you take with high probability over the Haar measure. If you take a state from the Haar measure psi and you trace out B, then this is close to maximally mixed in the following sense. Where these are the local dimensions, right? So okay, so local dimensions the A and the B, and then as soon as for any subsystem we break any way we want the total Hilbert space into two subsystems A and B, and it doesn't matter how we do it as long as the dimension of the system that we keep A it is slightly less than the dimension of the system we trace out. The reduced state on A is very close to maximally mixed. Okay, but of course this radiation that is coming out right at each time where it's coming out is a tiny system, right? So it's indeed compatible of this being like just maximally mixed, which is like thermal, right? Radiation at some well, there is no Hamiltonian here, right? So this is a toy model. Basically, we don't have energy here, right? Of course, once you put energy constraints, instead of getting maximally mixed states, we will get some thermal state that's some Hamiltonian, right? But because you don't do that, then there is no temperature, or temperature is infinite here, toy model, and therefore, right? Even though we can have a global state like this one, which is pure, right? But locally, it looks just like random, right? So maximally mixed, and this would explain why this Hawking radiation looks like thermal, even though in the process we get back psi-f. Okay, so that was like the motivation for this toy mod. So kind of it explains the story for now, but let's go one step more now. Is that clear? Is there any question or what we said last time? Arbitrary. This works for any way you partition this. Yes. Well, we are going to apply in different ways, but at the moment, the way we are splitting, you could say that A would be just one Hawking radiation, right? One qubit of Hawking radiation, and B will be all the rest. And this will explain why, if you just look at this, it looks like thermal, right? But later we're going to apply in different ways. This is a general result. It works for any way you do it. Okay, so now let's again analyze it. And now suppose we have our state that we put in. The black hole is there. It hasn't evaporated yet. And now suppose we just prepare some quantum state phi. Alice has it. Some observer has it. And we just send it inside the black hole. Okay, it's just a 1 qubit state. So this is a 1 qubit state. So what we know? We know that for an outside observer, right, this state will come in, and after a long time, you come out as Hawking radiation, right? And you'll be in some scrambled way. You'll be like in some entangled states, like with some other Hawking radiation. But we could decode it. We could apply some unitary and get it back. Okay. So we will analyze this in more detail, but that's what we have, right? This state gets in, after a long time it gets out. On the other hand, for someone that's getting inside the black hole, if they stay like Alice, would jump inside the black hole, they stay there, and it stays there inside the black hole, right? You still have this qubit there inside the black hole. So it appears that whatever dynamics is going on here, we start from some phi, and then after some time you get some phi inside the black hole, right? So inside, and you get the same phi outside, right? After it has irradiated, right? After it has radiated as Hawking radiation. But there's a nonlinear process, right? That's not allowed by quantum mechanics, right? This is called like non-cloning. So it appears that fishy going on here, right? Because you can do cloning of information, right? That qubits, there will be a copy of it inside and another outside the black hole. Because this qubit get inside the black hole, and once inside the black hole, it's there, right? For someone that is inside, because there's nothing unusual happens here. This right horizon until it hits singularity, right? Then we don't know what happens. But we also know from this argument that just give that it has to come out eventually, right? Because quantum information is preserved, right? The whole creation and evaporation of the black hole is a unitary process, right? So if you wait long enough, if you wait until it gets out, you have a copy of it outside, but also one inside, right? So I haven't told you, right? But that's something that is impossible. And one way to see that, and let me make the connection because we're going to use that later in a more elaborate version of this, is that this is impossible basically because if we could do it, you could violate this like monogamy of entanglement that I explained, right? So it's basically the same thing. So you just imagine now that you prepare a maximally entangled state of some reference with A, okay? And suppose there was a cloning machine. There was a machine of this form. Now you could apply this cloning machine, right, from A to A1, A2, and just get some states, right, R, A1, A2. But now because it's a cloning machine, right, and this reference, R would have to be maximally entangled with A1, with A2, right? Because it was original with A, right, and now we just clone, right? So imagine we have R maximally entangled with A. Now we apply cloning machine here, so now we have R maximally entangled with two states, which we know it's impossible, we saw before, right? So again, another way to say that is that it appears there is some of monogamy of entanglement here, right, if in this thought experiment. Is that clear? Any question on this? Yeah, but for whatever phi you're given, right? If you, for a given basis, you can do that, of course. But this is like for every phi, there's no linear process that does that, right? Yeah, it gets one particle, outputs two particles, yes. And both in the same state as the original one. But then there's no way you can do that for some arbitrary state phi that you don't know what it is, right? That, for particle is fine, yeah. Particle is fine. Yeah, sure. Well, yeah. Because if you know they said you can prepare as many copies you want from it, right? If you have a classical description. But here you don't, right? Whatever. Doesn't matter what the state is. Yeah, so suppose you have this cloning machine existed, okay? Now just get a maximally entangled state between R and A1 and apply the cloning machine to A1. Now you get another copy, A2. But you know, it's the same states, right? You should, now this was maximally entangled with that one, this one has to be as well, right? Well, no, because suppose you had this operation, right? So now, if this is entangled with something else, right, you would have to, you would preserve the entanglement with the other system as well, right? But anyway, it doesn't exist, so it doesn't. Yeah, it's and if you source like this, you can do many weird things, but that's one of them, right? So it's just because eventually we're going to use monogamy of entanglement for another paradox, but I just want to connect it. It's kind of related. But there's a solution to that, at least one possible solution, and this is was proposed by Susskind Toft, which is this black hole complementarity. And what they say is that actually there is no way we can access these two qubits at the same time, right? At the black hole, and then you cannot go outside anymore. That's it. Access to the inside. So actually, you should think as this apparently violation qubits as the same qubit, but just two representations of it. Okay. There is quantum gravity, we don't understand it, but for example, let's take some inspiration, for example, for ADS-CFT. Then there is a description of the theory, is non-local this theory, and then there is some redundancy of information here. So the physics outside the black hole, there is some corresponding physics inside the black hole of it, but it's really the same thing, just two different representations of it. Okay, it's a bit vague, and indeed it's vague, but at least was getting rid of this problem. And the main point that if there is no experiment that you can propose where we can verify this violation of monogamy of entanglement, or of non-cloning, or of monogamy of entanglement, you shouldn't care, right? So, you know, the fact that there is this two representation this was then, right? They thought this was the solution, and for a long time it seems that everything worked. And then until recently, right, there was this paper, AMPS, Marlov, Polchinski, and Sully. So basically tried to get a thought experiment where you could observe either violation of non-closure or actually they do in terms of monogamy of entanglements. Okay, and then that showed there is a big problem, right? Because there is a thought experiment where, in principle, you could execute it and you would see that something very strange is happening. And now we don't know what is the solution to it. And, I'll tell you some proposals which related to quantum computing, but I want to explain this first, right? How you get this beta paradox. Okay, so let's consider black hole again. Okay, and now let's consider the pure states. So this is the state of the black hole at some time. So of what is inside the black hole and of the Hawking radiation that are already left, right? So let's call H all the qubits which are still inside the black hole. Let's call B a Hawking radiation that just left, that we care about. And let's call R the early Hawking radiation, all the qubits that left before B. Okay? And we know if we believe in unitarity, the whole state is pure, right? Qubits inside the black hole, B is the Hawking radiation that just left the black hole, and R is the early Hawking radiation. Right, so like that. Good. So now we are going to see the math now in the Sigma. Let me just tell you the argument first and believe what I say to you. First, imagine there is an old black hole in the sense that more than half of its mass has already evaporated. Okay. Then, because of this Paige calculation, right, using this toy model, we expect that the reduced states of the total states on H and B, this is like less than the total number of qubits originally in the black hole. This plays the role of A here in this theorem, these results, and this is close to maximally mixed. Okay. So we're using that, right? And using that is an old black hole. So this is true for old black hole. But now there is a result. We are going to see it. It's called Illumise Theorem, if you heard of, which shows that this implies, actually, that you can take the state psi, HBr, and you can apply a unitary or isometry in general from R. It maps R to two subsystems of R. Let's call it RB and RH. So this implies that there exists this isometry U from R to RB RH such that U and identity on identity on HB psi. This will give a purification of each one of them. So this will give a maximally entangled state between H and HB, and this. So these two are and RB, RH. Sorry. These are just two subsystems, right? So this is just a split of the Hilbert space of R into two tensor factors, and another maximally entangled state of B with RB. Okay, we are going. Psi is the state is the total state of the universe, right? Because our universe only has one black hole. That's it. But right, so it has the stuff inside the black hole, has the B which just left the black hole, and has R, which is the early Hawking radiation. And now because of this Paige calculation that we did there, because it's an old black hole, the reduced states of the stuff inside the black hole and of this Hawking radiation that just left has to be close to maximally mixed. Okay. But now there is a result, we're going to see it in the table, is Illumise Theorem, which says that this implies that there is some U, a unitary, which you can apply to R, which makes this tensor product of maximum entangled states between what is inside the black hole and the early Hawking radiation, and a 2-qubit maximum entangled state of P with some subsystem here. Okay. And now, what is for the experiment that Alice can do? So, so Alice waits until it's an old black hole, right? So this just happened. We have this situation that I wrote there, and then she has some quantum computer. She has access to all the early Hawking radiation. She just collects it, right, patiently. So she just applies U here, right? She applies U, and then map it to some kind of this situation, right, where like inside a black hole is maximum entangled with this RH, and this B is maximum entangled with this RB, right, that she has, right? Codes this EPR pair, right? Applying this unitary, she can do it's outside the black hole, but now she just has a 2-qubit state, and she jumps inside the black hole with B and RB, okay, with these two qubits. And they are very close to maximum entangled states. But now there is a problem, right? And the problem is this view that I mentioned before, right? So there is a particle inside the black hole, actually. Let's call B prime, which in the calculation we did, this Hawking radiation is due to the creation of these like maximally entangled states of B prime, right? That's what quantum field theory tells us, right? So from so we find that B is maximally entangled with RB, and the same time B is maximally entangled with B prime, right? This is what quantum field theory calculation tells us, right? And this we just derive basically from basic quantum mechanics, right? From unitaries. So we have a contradiction, right? So okay. So and what is something else that we use is that there is a smooth horizon here, right? So she decodes this, she jumps in, so she should be alive here just to have the systems at her hands and see that something wrong happened, right? So we also need the horizon is smooth. So we have, right, so these three assumptions, and this maybe you can call effective, right, because this is just the quantum field theory applies so far from the singularity is a big black hole. So we have these three things that they are incompatible, right? So the conclusion is that this is incompatible. Okay, so something has to give, and that's why it's called firewall. So say, okay, actually there's just a firewall here. She can never realize that because there is a lot of energy here. She just gets burned down, right? If she gets inside. But that's kind of, who knows? But that's the moment. Okay, so the problems of the black hole, they are intentional basics of quantum mechanics, but now in a much operational way. Right now there is a thought experiment that in principle we had a violation of monogamy of entanglement of 3 qubits, and Alice so ways out, well, you could say maybe the unitarity is just wrong, right? Maybe you give up this. Maybe it's intrinsic decoherence in the black hole, some source of entropy. Okay, fine then. Theory is wrong. That's weird too, right? Because we know the effect of gravity is very, very small here at the horizon, right? Because gravity is very big here. So we know quantum field theory well, right? So and there's this again calculation. We don't expect that to be the case, right? So again, it's would be a so we don't really know. So it's kind of it's confusing. It's a situation. proposed, which is that somehow this idea of complementarity still holds here, but in a more way. And I want to get to that in the end of the class, because that's related to quantum computation. It's basically some proposal which says that actually the process of applying unitary, okay, this U, to the codes, this ZPR, actually is a very complicated quantum process. So if you want to physically, this will take a very, very long time, and the time it takes for this to be applied is much longer than the time it takes for the black hole to evaporate. So you never see a contradiction. Okay, so it's kind of, you look at the best way to implement this physically, to undo, right, to apply this unitary, and argue that it takes a very long time. We'll get back to that, but I want to show you some math now related to this now. Any question? Okay. So, right, so, well, I shouldn't have erased it, but now I'll just show you how this is done. So how we can show that with high probability over the Haar measure, with high probability if you take psi AB at random from the Haar measure, uniformly from the Haar measure, then it's very close to maximally mixed. Okay, which is this calculation kind of essentially done by Paige. But I'll show you a different way of showing that, which is a calculation with something very similar to this all the time in quantum information. Like if you understand entanglement distillation of mixed states, for example, this kind of techniques is the one that gives the best rates that we know. I'll mention it later, but let's see how we can do that. So that's what we eventually want to show. So let's start with something else. So let me just take the expectation value, this is the average, over pure states from the Haar measure. And I want to compute the purity of the reduced states. So I take rho A, I take the square of rho A, I take the trace and compute the average. Okay? I want to show you how to estimate this first. Who has seen this? No one? Okay. That's, yeah, there appears a lot in quantum information. How we do that? Well, the first idea is to do something that we call the swap trick. So the idea here is that we write this, we keep the expectation, fine. But we realize that this square, right, is rho as follows. So you can write it as rho A tensor rho A dash, a copy of it, times what we call the flip or the swap operator on A and A prime. Okay, so that's identity. What is this guy? This is just the flip operator of two vector spaces. It just swaps. So if you apply this to a basis xy, or to some element xz, it just gives us zx. Okay, it's just the matrix that swaps the two vector spaces. And that's opposite. So the fact that this is equal to that is true for every. Okay, so that's an easy calculation you can just check. So we can write explicit this by what is this swap? It's equal to sum over ij, ji. That's what it does, right? It's just if you swap a basis, you swap everything. So that's what it does. And exercise verify this. Okay, using this representation. Just write this in some basis, and you see that this holds true. I'll leave it to you. Okay. So this is good, because now we can continue, and this is equal to the same expectation, right? Again, this is just the average, right? It's the average over states of the Haar measure. And now we can more write this as trace like that, right? So if you take the global trace, the total trace, you can take first the trace over B, then the trace over A's. The trace over B, there's identity here, so it's just the trace of this guy over B, which gives row A tensor row A, right? So this is on AB, and this is on A dash, B dash. Okay, is that clear? Okay, now we can put the expectation inside, and now there is a useful identity, which is the following. If you average over the Haar measure, this guy, we get, of course, a mixed state, right? And it's a mixed state, special one. Anyone knows what it is? Probably haven't seen this before, but just in case. We get the maximally mixed state on the symmetric subspace of these two systems, AB and A dash B dash. So what is the symmetric subspace? You get identity, okay? Identity on AB, A dash B dash, plus the flip, but not the flip between AB versus A dash B dash, and we have to normalize. What is the dimension of identity? It's just, right, the total dimension of the space. So it's, remember, A is isomorphic to A dash and B is isomorphic to D dash, so it's this guy square, this square. What is the dimension of this? Well, you can compute from this representation, and you find that it's just dA times dB. Okay? So that's an identity that you can show. I will not have time to prove it, but let me just give some arguments why this is correct. Imagine that we get this state, right? That's our state, let's call it X, okay? And suppose we just apply for any unitary, we conjugate by the unitary. Okay, we do that. Then this gets inside, and we apply U to each psi, right? So we just change psi by U times psi. But this is the Haar measure, so it should be uniform, right? So it should be invariant if you apply a unitary to it, right? Because it just measures the points. We average over all points in this sphere. If you just rotate all the points by some amount, the average is still the same, right? It's rotationally invariant. So this has to be the same as X, okay? And this has to be true for all U. For all unitaries, U unitary. Which is the same as saying that just X has to commute with U tensor U. So now that's the part I wouldn't have time to prove, but now you can use a group representation theory, right? So now we have representation of the unitary group, namely the representation where you get two tensor products of it, of the same U, and we have something, the commutants of it, right? We have something that commutes with all elements of this representation. But now, what you can do, you can just write this reducible representation as a direct sum of irreducible ones. And you can compute the irreducible ones will be exactly the representations that live in the symmetric and the antisymmetric space. But now, because this is in the commutant, you find, doing that actually X has to be equal to some coefficient alpha identity plus beta flip. Okay? So the fact that guys of this form are preserved, that's easy, right? So suppose you have identity and you conjugate. This gives identity again, right? But flip also does it. Suppose you have the flip, right? Or even the commutator. The flip here just change the two copies. So again, it's U tensor U, right? So it's clear that everything of this form is invariant under these guys. But the interesting is that these are the only things which are invariant. Okay, so this takes a little bit more work to prove, but it's true. So we know that whatever average is here, it must be in this form, alpha identity plus beta flip. So now we have a system of two equations, and this system of two equations you can just solve simply by saying, okay, what is the expectation value? These are linear independent, right? So just computing the trace of this original guy with identity and flip, you can solve the system of equations, right? So it's easy to compute this expectation value. They both give 1 here, right? The expectation value, trace of this guy with identity is 1, and trace of the guy with flip is also 1. So we solve the system of equations and we find this. Okay, it's a bit. I went a little bit fast, but this will take us too long to do it slowly. So it's something you can accept, or something you can try to figure it out. But it's right. That will be the right thing, right? Okay. Any questions here? Probably I went too fast. So now let's just use it, right? So let's just do the computation. Now it's easy. So first, actually, we just use that this guy has a nice representation. So you have the flip of A and B with this guy. That's the same thing as flipping A with A dash, tensor products flipping B and B dash. Okay, that you can also check. It's easy, and we're going to use that. What we find? We find that this guy will be equal to times what I had before, right? Okay, is that clear? I just so this expectation value comes inside, right? We get this guy. This is equals to that. I replace this here, and we still have to compute the trace with the second term, right? So this has two terms. Let's compute. So the first is just trace of this guy. Okay. This is something that I'll leave for you to check too, but it's easy. That the trace of the flip actually is just. So we're going to use that. This term, we just have trace of this guy divided by this factor. The trace of the flip is dA. So it's tensor product. So the trace of the tensor product is the product of the traces, right? And the trace of the identity is dB square, because it's the identity on B dash. This divided by, which we can write maybe as, no, let's leave that. So dB. And now the other one, the second term, we have to multiply this by this and take the trace by flip. We just flip twice. This should be the same as identity on A dash times flip on B dash. It's the same calculation again. So the identity term we get dA square. From the flip we get dB. Okay. The dimensions are pretty big, so more carefully, but just to be quick, this dominates over this, right? There is square and these dimensions are very big. So this, let's just, if you don't, there will be a subleading order which goes like square of the type, something like this. So this is roughly just this guy divided by the first term, which gives 1 over dB, plus the same thing for the other, which is 1 over dA. Okay? So actually, if you do like that, it's roughly this and subleading corrections which are much smaller, right? They go over dA square or 1 over dB square, something like this. Calculative. Okay, so that's okay. We have estimated this, right? Continue to prove this. Is that fine? Okay. So now to continue, that's the only calculation you have to do. So now I claim that this implies that. Okay, that's the claim. Now we just have to play with norms to see that. Okay, so now let's start playing with them. So first we have to introduce this Frobenius norm. It's basically the Euclidean norm if you treat x as a which has this form. We take x dagger x, and outside the trace we take square root. Okay, remember the trace norm was the square root inside the trace, right? So that's the difference. And now we can suppose we look at this difference of row A and identity divided by the A, but we look at the 2 norm square. Okay. Then now it's easy because there is not square. So basically we just take trace of this guy square, right? Of this decompose into 4 terms, right? One term is trace row square. And then there are 3 other terms. One term is trace identity maximally mixed square. So this gives 1 over dA, right? And the cross terms, you multiply row A by identity over dA. Then you just get, right, row A over dA. You take the trace, you get 1 over dA as well. But now because, right, it's twice this term with a minus sign and the other with a plus sign, this just gives 1 over dA. So do the calculation yourself, you'll find it, right? Great, but now we have this, right? So what this implies? This implies that the expectation value over psi from R of this guy that's smaller than 1 over dB, right? Okay, so just use this calculation, right? A cancels and we get this. So we're interested in trace norm because that's the useful one, right? That's what we saw before. But we already see that the Hilbert square, the expectation value is very small. The average is very small, right? And now we want to connect the two. So now we use this result. Which is that the trace norm of some matrix X is always smaller than the dimension, right, of X times, or if let's just put like X on A, so dimension of A square root times the 2 norm. Okay. Why that's the case? That's easy to show actually. So we already learned that this is equal to maximum over actually what I told you before, this is equal to the maximum from 0 to 1, 2, but that's the same as going from identity to minus identity without the 2, right? That's kind of equivalent. Trace mx. Okay, so that's this thing. Now we can use Cauchy-Schwarz, right, for the inner product of matrices. That's always smaller than the 2 norm of M, the 2 norm, right, of X. But now we take a 2 right, so let's estimate this 2 norm. 2 norm square equals trace M square, because that's Hermitian. But that's always smaller by this quantity than trace identity, which is dimension, right? Okay, so we take the square root, right? And we find. Okay. So why are you doing all of this? Well, what was the point? So we want to estimate maybe the expectation value over this trace norm. But that's very complicated thing, right? So that basically, remember this guy, just to compare, the trace norm has the square root inside the trace, right? It's like the square root of the operator. And we have no idea how to compute the expectation value of the square root of the product of operators. So that's very complicated. We don't know how to do that. We do know how to compute the expectation value of the square, right, of this. This we won't know how to do. So first, 2 norm, because the 2 norm, it's much nicer and it relates to form. We compute there, and then we have to go back to the complicated norm. But in doing so, we lose a little bit, right? We lose this. Fortunately, in this case, it works out. It's fine. So, so let's see it. So let's put everything together. So we find that expectation over R let's compute the average square. Now, square is a convex function, so that's always smaller than the average of the square. Now we use this bound here. Okay. So that's always smaller than dA times expectation value this guy square. Okay. And now we use the bound, this one. Right. So dA dB. Okay. And now we can just take the square root on both sides and recover this. Although here I should have been more careful. So the statement we just prove is the following: expectation value over psi har is small, right? Now, how we can get from this to high probability? Well, you know, it's a norm, so they are all positive terms, and we know the expectation value is small. So the only way that the expectation value of some quantity which is always positive is small is if it, at almost every point the quantity is small itself, right? So you could map this into a statement saying with high probability, just use it like Markov inequality, for example. So we can show that with probability bigger, that the set of points for which trace norm bigger than this thing times 1 over c, that's smaller than how do I do that? Yeah, the probability of this quantity which is bigger than this times c, this is smaller than 1 over c, right? That's what you get from Markov, for example. So this is trade-off, but you can just in terms of saying just the average of this thing is small and is equal, you know, is bounded by that. Okay, so this sometimes people call Paige Theorem, right? Because he was the first one to do this calculation for like high random states, exactly next to this black hole problem, right? So he did that in a slightly different way, but yeah, that's what he got. Any question? Right, so this was one thing that we needed that I mentioned before, right? So remember, let me just remind you what was the problem. We had the state of the black hole, which was inside the black hole. I call it H, right? B, which was the Hawking radiation, like the recent Hawking radiation. And we had R, which was the early Hawking radiation, right? Everything that came before. Right? And it was a old black hole, so R had more than half of the qubits, right, of the black hole. So what we just proved, now indeed is a proof, right? If you take the reduced state of H and B, that's very close, with high probability, that's close to a maximally entangled state. Sorry, to a maximally mixed state. Right? Everyone is with me? Right, you just did that. Now let's go to the second point that we needed. Now we want to argue because of this. H must be maximally entangled with a subsystem of B must be maximally entangled with another. And that's a general statement of quantum information, of quantum mechanics, and is very useful in other stuff as well. It's called Illumise Theorem. There is some exact version that we're going to prove. There is also some approximate. It's not proof, but I won't do it. But it says in words basically the following. Suppose you have two pure quantum states on A and B, and suppose that the marginals of these two states on A is the same. Then the two states must be the same B on the predefined system. And if they're just close, they have to be close globally as well. Okay, so let's go look at the exact case first. Suppose psi AB and phi AB, they're such that the margins are the same. So okay, then we are going to show this now. There must exist a unitary on B such that psi B equals identity on A, U on B, phi AB. Okay? And this if and only if, of course, right? So clearly, if that's the case, suppose that's the case, and we just trace out B, right? Then okay, we get the margin of psi, but here we get the marginal of phi, right? Because it doesn't matter. We're tracing out B, so if we just do a rotation, it doesn't change anything. So the interest direction is from here to here. Who has an idea how to show this? Think about it. It's not too hard actually. And only uses things that saw here in the previous days. I'll start doing and then you help me. So let's look at Schmidt decomposition. Okay, so we have psi AB. Let's know by rho A the marginal, right? Actually, before Schmidt on Schmidt decomposition, what was the idea? The idea is that we can write this in the following form as I lambda I. Let's write it. I where is what? This is a basis, but it's a basis. How we get this basis? Who remembers? Yes, but in the SVD you can relate to the basis of the reduced states, right? So if you trace this out, what is the reduced state? Is this guy, right? So this is the eigenbasis, right? The eigenbasis of the reduced states, right? And these I should call like, right? Because they can be different eigenbases, right? But eigenbasis of these guys, right? Okay. So great, but now we know that rho A is this guy. But now we know this is the same as trace phi, right? And this phi we can also write some Schmidt decomposition. Well, okay, it's the same as that, right? But then this shows, right, that the Schmidt decomposition of phi should be something like should be something like this, right? With the same basis here, right? Because this base is given by the reduced density matrix, but they have the same reduced density matrix, right? But of course, the basis on B, they it's different, right? This we don't know, right? Because we don't know about B. Found that, okay, we can write the states, the lambda i's are the same, the eigenvalues of the reduced density matrix is the same, because the marginal is the same. The basis on A is on B, it can change. But then we're done, right? Because we just have to change the basis on B, right? So just define a unitary which on B, right? We change this basis. It goes from this prime, what I call prime, to the dash, right, on B. And by there, if you apply this to psi, we get phi. Right? So you can do it yourself, right? So you do there, right? This is the basis of organoid H1. This is another one. So you just basically here put the prime if you apply the unitary, right? Which gives phi. Okay. Any question on his? Okay, good. So that's the exact way. It's pretty easy, right? So it's just really Schmidt decomposition that we saw before. There's also the approximate version. I won't prove, but it's true, which basically says that suppose now that this thing are just closed. Then it says that there exists a unitary such that the pure states are closed. So such that this is smaller than, and then maybe you heard of fidelity. Fidelity is another way of measuring how close to quantum states are. This is the most elegant state in terms of fidelity, because then the epsilon you have here is the same as the epsilon you have here. But I'm using trace norm just because you're introduced, and I don't wanna introduce a lot of stuff we actually don't need. Then in that case, it's a little bit more ugly, but it's more or less the same. It's 2 times square root epsilon. Okay, but the point is that if epsilon is small, this is still small, right? So that's how we're going to use it. All right, so this is what we call Illumise theorem, right? So that's the approximate version. So Illumise theorem. Right, so so let's go back again to the problem, right? I already erased, but we had the black hole, early, what is inside, what just came out, and the early Hawking radiation. And we know that if we trace out R, the old Hawking radiation, this is maximally mixed. Right? So now we want to apply this result. So how we apply the results? Let's consider 2 purification. Oh, and we know this is close, right? Actually, right? Because the calculation was just show that not the same but close. So let's apply this result where psi is psi, and where phi is the purification of this guy that I'm going to write. So first let's apply this result where the subsystem A will be equal to HB. Oh, well, okay, this will work because I have B here as well. But so I won't write for confusion. But right, there is always a bipartite split, and this will be one party HB, and R will be the other. So this is psi and phi. I'm going to write this R as two subsystems, R1, R2. Okay, so we think that the Hilbert space, well, let's notice the Hilbert space of R is isomorphic to a tensor product like that, and this should be HR HB. So I define phi as follows. It's just a maximally entangled state. Remember, this was the maximally entangled state from before, between H and RH. Sorry. Tensor maximally entangled states of B with RB. Okay? So what happens if you trace out HR and HB here? What do we get? Sorry? Let me write. So what happens? We trace out RH, R sub H, and R sub B on the state phi. What is this state? So there's a product, right? So we can trace out this. What do we get if we trace out this? Maximally mixed, right? Yeah, so. And now we trace out this, and we get maximally mixed again, right? So this phi that I constructed is a purification of this, right? Of the right-hand side, right? On the other hand, psi, the original state, by construction, is a purification of rho, right? So now this, right? So this says that there must exist a unitary U, and now it's a unitary, right? Remember, we have this thing, right? So it's a unitary on R to RB RH, such that we apply the unitary. Let's write that from R. We do identity to HB. Maybe it's better. The other was the other one. So we do nothing to HB. We do this U from R, RB, RH. We apply this to our original state on HBR, and we get close, right, to purification of the right-hand side, right, which is this guy, right? So we get a maximally entangled state between H and RH, and a maximally entangled state of between B and RB. Okay? And this is what we want to show, right? This was the thing from before. So remember, this is the Hawking radiation that just came out. This is one qubit, which is maximally entangled with it, which is we decode, at least get these things, and jump in the black hole, right? So that was the technical part that we needed. So this is how you show it. Okay. So not there are two directions that we can take. We'll take both, but let me just. One thing is just to finish this discussion of black hole. Right? We can say, okay, what is the copped out now, right? That people do. So there is this 4 experiments we just saw in detail, right? How you lead into this, right? Tension between these 3 things that we forward through. One has to give. Then now the question is if we can recover complementarities in some way, right? It is the case that for some reason we cannot have these 3 particles which would violate monogamy of entanglement together at the same time, right? And there was a proposal for that. And basically what they say is, let's go back here. So what is the 4 experiments? In the 4 experiments, Alice, the experimentalist, she collects all qubits in R, right? She just has this big memory. She's getting all this quantum information, and she's storing some quantum memory. This is R. Then she waits until she gets B. She gets B. Now she has to apply some unitary here, so she has to do some interaction here between B and R. This is U. After she applies it, she has now these 2 qubit entangled states, and she can jump in the black hole. She has to look for the partner of B, this B prime, right, which is this local entangled states that follows from this fluctuation of vacuum, and she'll be able to see that there is something off there, right, because she has the 3 particles at the same time. Now, what is the? This is fine. This 4 experiment is fine, but what we haven't considered is how long it takes to apply this U, right? We just know Ullmann's theorem tells you it exists, but we don't know how long it takes to apply it, right? So, so the question they ask, Heide and Harlan, is how long it takes to implement U. And the U is like they call Hawking. You can call this like the Hawking decoding problem. Right, so basically you want to decode this E-bit of entanglement that you have between B and some other qubits in the early Hawking radiation, but which is very scrambled, right, with the other qubits of early Hawking radiation, and you have to implement this U, which decodes in from there, right? Then there's no proof. There is like a belief, maybe you can call, that would explain things at least, well, partially. So the belief, and that we can discuss why we think that's true, is that it takes exponential time in number of qubits in R to apply U. Okay, but now suppose that's the case, right? That's the case, then there is no way the thought experiment doesn't work, right? Because you have the black hole at some points. Again, you have this HBR. Now Alice starts applying the quantum. Has a quantum computer, start applying the quantum computation, which will do the Hawking decoding. But while it applies, this black hole evaporates and evaporates more, right? And after the time scale is such that after she finishes, the black hole is not there anymore, right? Because the time of the black hole to evaporate goes something as evaporation time, goes as the number of qubits in the black hole to the power of, okay? And under the assumption, the decoding time will be like exponential in n. Okay, so it's a weird way of recovering this complementarity, right? Because there is a form that which you could do, and there will be a problem, but to do it, you need to apply some very complicated physical evolution in a much shorter time scale that it takes to apply. How could you do that in? For example, you could put a lot of and you can do it faster, But if you put that much energy, right, then at some point where quantum gravity should hold, right, where it has visible effects, then indeed, then everything can happen. You don't know, right? So when in the dream, it's at low energy, away from the singularity, right? And you have to be subtle not to create a black the quantum computer, right? In a way, which you do, right? If you put a lot of energy, then it takes a long time. Excessive. It's like complementary again in some subtle way. Now, why I want to say that? Well, that's nice because that takes us to is a motivation to try to make it more rigorous. What I mean by that, right? What I mean by having some qubits to apply, right? So how we have a model to make sense of it, and then this is a part of that we have is very important in this connection of quantum computing and physics, and which maybe I'll talk more. Well, I'll talk a little bit now and more tomorrow, which is right. So far we have talked a lot about entanglements and so on, and Burak as well with tensor networks. But let's talk about quantum computation now, right? So let's look at this view where we look at dynamics and we see how we can break it into like some easy quantum interactions, small quantum interactions, and how can we have a theory around that, right? Very nice, like, I don't know if this is true or not, right? After some stuff I have to tell you, I'll tell you some intuition why it might be the case that this U takes a long time, but we don't know. It's a very nice way of putting together basically computational complexity theory, right? And right, in a sense, quantum gravity, right? Which is something new we haven't seen before, so I think it's an interesting proposal.
Interesting because it kind of promotes computational arguments
Yeah.
to sort of physical acts
Yeah.
in a sense, right? So
Well,
you have a problem
yeah.
with the physical axioms that kind of are inconsistent with each other. Now you bring up a computational complexity.
That's right. That's right. It's something new. Never. Yeah.
Graphically, it's interesting.
That's correct. Yeah. And that's why complexity theories, of course, they love this argument, but
Unsatisfactory from
yeah.
the view of the physical axioms in a sense, in the way we're traditionally used to.
I agree, but I think about it is really like this, right? That we have this from nature on the speeds that we can apply at 2-qubit gates, right? Too fast, you just need too much energy, and then you can reach there, but then it's quantum gravity again, right? Where we don't want to touch because there, right, we don't understand, right? This is a fundamental limitation on the time it takes to apply this if complicated.
But then we arrive at the situation that many unitaries are unphysical. Never see them, we will never be able to apply it.
That's right, and indeed we think it's one of them. Basically, this complexity of this decoding U is exponential, right?
You say that there is something wrong with orthodox quantum mechanics. So in the axiom mechanics, all
Yeah.
unitaries are physically possible, right? But now we are starting to see not unitaries are physically meaningful. Right?
No, they are all physically meaningful, but if you wanted to, yeah, you're right, but there is this caveat in this problem that we must stay within low energy physics, right? So that's a limitation, right? Because remember this paradox only came about because we insisted, for example, that the horizon was smooth, right? And the quantum field theory applied there, right? If we are in very high energy physics, this simply might fail, right? And we are happy, right? But that's why this is kind of makes some sense, right? So it says that if we're within low energy physics, this takes a long time to apply. We never, this thought experiment, we are back to the complementarity view, right? Where these 3 qubits, which indeed in principle they would violate small logarithmic entanglement, actually 2 of them we should see as the same one, right? In 2 different representations, right? And we never have access to them at the same time. But at the same time, I'm very sympathetic to it. It's like, yeah, it's something very they will usually think, and that is worth thinking more if it really makes sense. And many people are doing that. I don't think there is a consensus yet, right? But yeah, okay. So Right, so circuit model, I don't know if you were here for this talk that I gave yesterday, but I discussed this very briefly, right? But now I want to discuss it more carefully. So suppose you have a unitary, U. So it's a unitary on dimension 2 to the n, okay? So it just corresponds to a unitary on n qubits, right? This is the dimension. And now let's look at special unitary. So you have the n qubits here, okay? And let's first look at unitaries U, which can be decomposed as V1, V2, up to some V, let's call capital N, where each one of these V's, it has to be a it can only act on 2 qubits at the same time, okay? So V1 can be an arbitrary 2 by 2 qubit unitary acting here, then V2 can act here. They could act on nearby, but doesn't matter. We can also just say that they can only act on nearby. So, and so on, right? Suppose we look at this class of unitaries, and we say, okay, n, we're interested in when n is some polynomial of n, of small n, okay? Unitary is what we call polynomial time quantum circuits, okay? And maybe what we call the quantum strong Church-Turing hypothesis. Tells us that this is really, at least one possible model, is equivalent to the notion of efficient computation in the universe, right? This describes efficient computation in our universe. Right? So it's a long hypothesis, right? Because there is many variants. So Church-Turing hypothesis, or actually, sorry, it's not hypothesis. It's thesis. Sorry, because it's more vague, right? It's thesis. So this Church-Turing thesis just says that anything you can compute in the universe, you can compute by a Turing machine, or equivalent, you can compute by some classical circuits. That's another variation. And as far as we know, it's true. We don't have any contradiction to it. But then there was another version, which is the strong Church-Turing thesis. And this was saying that everything that you can compute efficiently on the universe, you can compute efficiently on a Turing machine as well, right? In the sense that if you had some model of computation that could factor, for example, in time n, then on a Turing machine, it would take time at most n to the k for some constant k, right? So you allow some polynomial overheads, some polynomial slowdown, but wouldn't ever be exponential, right? So there was a long-held belief, right? People believed that until quantum computation came, right? So quantum computation, for example, Shor's algorithm, right? That I mentioned yesterday, it shows that this strong Church-Turing thesis, it gives strong argument that it's wrong, right? That indeed, if you have quantum mechanics, it's very different computational model if you concern time than if you have classical mechanics, right? Of course, in terms of computability, it's still the same, right? You can always simulate quantum mechanics classically with exponential overheads. So in terms of what you can compute, doesn't change. But in terms of time, there can be big difference, right? That's what we think now. But now you can just say, have a quantum strong Church-Turing thesis, where we say, okay, now quantum mechanics is the final thing, right? Maybe one day, yes. Yeah. Yeah, that's why it's a thesis, right? So, yeah, right, yeah. There's nothing proven. Yeah, sure. That's right. But that's what we believe, right? So, you know, until the time where someone comes with efficient simulation of quantum mechanics, right? Then it seems to be different models. One day someone might come with, but it seems unlikely from what we know now. But now we can say, okay, quantum mechanics is the final thing. And then if you want to understand efficient computation in the universe, that's the model. It's a very concrete model now, right? So we say that some you can encode some computation or just some physical process. We say we can do that. That's something that even like can exist in nature if it has a decomposition as a quantum circuit. And a quantum circuit, we break it into small blocks where each time only 2 or a few qubits interact with each other. And the path is not too long, right? The path is just like polynomial in it. Okay. So what is one example of such things? Well, it should describe at least everything that we encounter in physics, right? In everyday physics, and it does. So, for example, you can show that if you have just some unitary dynamics, where this is local, then you can approximate this very well with error epsilon by some v1, vn, where n scales as roughly number of qubits t log 1 over epsilon, something like this. Okay. So the circuit modeling definitely includes all just evolution according to local Hamiltonians. Includes more, right? Because we don't need time independence, right? It can change. But right, is reassuring that we have at least this. So okay, I'm almost out of time. But what we see next time, then we can start looking at unitary. I can give you a unitary on n qubits, and I can ask, is there a decomposition in this form, right? What is the shortest decomposition of it? Meaning, we write. So actually, we can write any unitary in this form if you allow n to be potentially big in the small n, in the number of qubits. But now suppose we look at what is given all the compositions of the circuit of the unitary as a circuit. What is the one with the shortest capital N? This is called the circuit complexity of the unitary, right? This is the most efficient way of implementing this unitary. And now what you can show, for example, for almost every unitary you can think, the circuit complexity is very, very big. Okay, it's exponential actually. So most of these unitaries, they're just an abstract notion, right? We never see them in nature, right? You cannot implement them. It will take like more time than the age of the universe, right? And this will be exactly the point. We think that we have to argue hand-waving. There is no proof that this U, because there is no structure of this which has very short, long circuit complexity. Okay, so this will be one thing that I want to do next time, and then we see some other applications of this to physics. Maybe I want to go a little bit to condensed matter that we haven't touched yet, but we'll see that next time. So that's all. Thanks.